When dealing with an existing generator already serving two life safety loads to separate buildings, adding an additional optional load requires careful consideration and adherence to electrical codes, specifically the National Electrical Code, or NEC. Given the existing configuration with two frame-mounted source switches located side by side without separation, there are a couple of viable options. Firstly, adding a third subpanel, and secondly, installing a transfer switch. Let's explore each option in detail. Firstly, consider adding a third subpanel. This involves installing a new subpanel adjacent to the existing two. The optional load would then be connected to this new subpanel. The crucial step here is to feed the new subpanel from one of the existing source switches. However, this approach necessitates careful evaluation of the existing source switch's capacity. Is it capable of handling the additional load without exceeding its rated capacity? This is paramount. If the existing source switch is adequately sized, this option provides a relatively straightforward solution. It allows for segregation of the optional load while leveraging the existing generator infrastructure. However, if the source switch is already near its capacity, this option might not be feasible without upgrading the switch itself. Secondly, consider installing a transfer switch. This involves installing a transfer switch that is capable of handling the combined load of all three circuits, that is, the two existing life safety loads and the new optional load. The transfer switch would be connected to the two existing source switches. The optional load is then connected to the output of the transfer switch. This approach offers a more comprehensive solution, especially if the existing source switches are not individually capable of handling the additional load. The transfer switch acts as a central point for managing the power distribution from the generator. It ensures that the generator's capacity is utilized efficiently and safely. However, it's essential to select a transfer switch with an appropriate rating to accommodate the total load. Several important notes are crucial for either option. The optional load should be classified as an emergency load to comply with NEC requirements. This classification dictates specific wiring methods, overcurrent protection, and other safety measures that must be implemented. The transfer switch must be interlocked with the existing source switches to prevent simultaneous use. This interlocking mechanism is critical to avoid overloading the generator and potentially damaging equipment. The electrical wiring must be sized appropriately for the load and comply with NEC standards. Proper wire sizing ensures that the conductors can safely carry the intended current without overheating, which could lead to a fire hazard. A licensed electrician should perform the installation and ensure that all applicable codes and regulations are met. This is non-negotiable. Electrical work, especially involving generators and life safety systems, requires specialized knowledge and expertise. A licensed electrician can ensure that the installation is performed safely and in compliance with all relevant codes. Diving deeper into the first option, adding a third subpanel, it is important to consider the implications for load calculation. The NEC provides specific guidelines for calculating electrical loads, including demand factors that account for the fact that not all loads will operate at their maximum capacity simultaneously. These calculations must be performed accurately to determine the appropriate size for the feeder conductor supplying the new subpanel and the overcurrent protection devices protecting those conductors. Furthermore, the location of the new subpanel must comply with NEC requirements for working space and accessibility. Sufficient space must be provided around the subpanel to allow for safe and easy maintenance and repairs. The subpanel must also be readily accessible, meaning it should not be obstructed by any permanent fixtures or equipment. Turning to the second option, installing a transfer switch. There are several types of transfer switches available, including manual, automatic, and bypass isolation transfer switches. A manual transfer switch requires manual operation to switch between the normal power source and the generator. An automatic transfer switch automatically switches to the generator when a power outage is detected. A bypass isolation transfer switch allows the transfer switch to be bypassed for maintenance or repairs without interrupting power to the loads. The choice of transfer switch depends on the specific requirements of the application and the desired level of automation. Regardless of the type of transfer switch selected, it must be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories, OIL. This listing ensures that the transfer switch has been tested and meets the applicable safety standards. When selecting a transfer switch, it is also important to consider the voltage and current ratings. The transfer switch must be rated for the voltage and current of the system to which it is connected. The transfer switch must also be capable of withstanding the available fault current at the point of installation. Fault current is the amount of current that would flow in the event of a short circuit. The transfer switch must be able to safely interrupt this fault current to prevent damage to equipment and injury to personnel. In addition to the voltage, current, and fault current ratings, it is also important to consider the transfer switch's withstand and closing rating, or WCR. The WCR is the maximum amount of current that the transfer switch can withstand for a short period of time without being damaged. This rating is important for ensuring that the transfer switch can withstand the stresses imposed during a fault condition. The installation of a transfer switch also requires careful attention to grounding and bonding. Grounding provides a low impedance path for fault current to return to the source, which helps to protect equipment and personnel from electrical shock. Bonding ensures that all metallic parts of the electrical system are electrically connected, which also helps to reduce the risk of electrical shock. The NEC provides specific requirements for grounding and bonding, which must be followed carefully. In addition to the technical considerations, it is also important to consider the cost implications of each option. Adding a third subpole may be less expensive than installing a transfer switch, but it may not provide the same level of protection and control. Installing a transfer switch may be more expensive, but it can provide a more reliable and safer solution. The best option will depend on the specific circumstances of the application and the available budget. Regardless of the option chosen, it is essential to obtain all necessary permits and inspections before beginning any electrical work. Permits are required by local authorities to ensure that the work is performed in compliance with applicable codes and regulations. Inspections are conducted by qualified inspectors to verify that the work has been performed correctly and safely. Failure to obtain the necessary permits and inspections can result in fines and other penalties. Furthermore, it is important to maintain accurate records of all electrical work performed, including drawings, specifications, and test results. These records can be valuable for future maintenance and troubleshooting. Let's elaborate further on the NEC requirement related to emergency systems, as the optional load is to be classified as such. Article 700 of the NEC covers emergency systems, which are defined as systems intended to supply power automatically to designated areas and equipment in the event of failure of the normal power supply. These systems are essential for life safety and must be designed and installed to provide a high degree of reliability. Section 700.12 of the NEC specifies the requirements for the source of power for emergency systems. The source of power must be capable of supplying the emergency load for a minimum of 1.5 hours. This can be achieved using a generator, batteries, or other suitable power source. If a generator is used, it must be equipped with an automatic transfer switch that will automatically switch to the generator in the event of a power outage. The generator must also be regularly tested and maintained to ensure that it is in good working order. Section 700.9 of the NEC specifies the requirements for wiring of emergency systems. The wiring must be physically separated from other wiring systems to minimize the risk of damage or failure. The wiring must also be protected from fire and other hazards. Typically, this involves using fire-rated cable or conduit. Section 700.16 of the NEC specifies the requirements for lighting for emergency systems. Emergency lighting must be provided in all areas that are essential for life safety, such as exit routes, stairwells, and elevator lobbies. The emergency lighting must be designed to provide adequate illumination for safe egress. In addition to the NEC requirements, there may also be local codes and regulations that apply to emergency systems. It is important to check with the local authorities to determine the specific requirements in your area. For example, Some jurisdictions may require that emergency systems be inspected and tested on a regular basis. Others may have additional requirements for the type of equipment that can be used in emergency systems. It is also important to consider the specific needs of the building and its occupants when designing an emergency system. For example, a hospital will have different requirements than an office building. A hospital will need to provide emergency power to critical medical equipment, while an office building will primarily need to provide emergency lighting for safe egress. When selecting equipment for an emergency system, it is important to choose products that are listed and labeled by a recognized testing laboratory, such as UL. This listing ensures that the equipment has been tested and meets the applicable safety standards. It is also important to choose equipment that is reliable and durable. Emergency systems are designed to operate in critical situations, so it is important to choose equipment that will perform reliably when needed. Let's consider some examples of how these principles apply in practice. Suppose a small office building needs to add an emergency lighting system. The building owner decides to install a generator with an automatic transfer switch to provide emergency power. The electrician calculates the emergency load and selects a generator that is sized to handle the load. The electrician installs the generator and transfer switch in accordance with the NEC and local codes. The electrician also installs emergency lighting fixtures in all exit routes and stairwells. The electrician tests the emergency system to ensure that it operates correctly in the event of a power outage. As another example, suppose a hospital needs to upgrade its emergency power system. The hospital decides to install a new generator with a bypass isolation transfer switch to provide emergency power to critical medical equipment. The hospital engineers calculate the emergency load and select a generator that is sized to handle the load. The engineers install the generator and transfer switch in accordance with the NEC and local codes. The engineers also install automatic transfer switches to power critical medical equipment, such as ventilators and heart monitors. The engineers test the emergency system to ensure that it operates correctly in the event of a power outage. The hospital also develops a comprehensive emergency plan that outlines the procedures to be followed in the event of a power outage. Let's now address the potential challenges that might arise during the installation process. One common challenge is dealing with limited space. Generators and transfer switches can be large pieces of equipment, and it can be difficult to find space to install them, especially in existing buildings. In such cases, it may be necessary to consider alternative locations or to use smaller, more compact equipment. Another challenge is coordinating the installation with other trades. Electrical work often needs to be coordinated with other trades, such as mechanical and plumbing. This can be particularly challenging in existing buildings where there may be limited access and congested spaces. Careful planning and communication are essential to ensure that the installation is completed smoothly and efficiently. Another potential challenge is dealing with unforeseen site conditions. During the installation process, it is possible to encounter unforeseen site conditions, such as unexpected wiring or plumbing. These conditions can require changes to the installation plan and can add to the cost and time of the project. It is important to be prepared for these contingencies and to have a plan in place for addressing them. Let's not forget the importance of proper maintenance and testing. Emergency systems require regular maintenance and testing to ensure that they are in good working order. Generators should be inspected and tested on a regular basis to ensure that they are capable of supplying power when needed. Batteries should be tested to ensure that they are holding a charge. Transfer switches should be inspected and tested to ensure that they are operating correctly. The NEC requires that emergency systems be tested on a monthly basis. The testing should be documented, and any deficiencies should be corrected promptly. In conclusion, adding an optional load to a generator with existing life safety loads requires careful planning and execution. It is essential to comply with all applicable codes and regulations, including the NEC. A licensed electrician should perform the installation to ensure that it is performed safely and correctly. The optional load should be classified as an emergency load and wired accordingly. A transfer switch should be interlocked with the existing source switches to prevent simultaneous use. The electrical wiring must be sized appropriately for the load. Regular maintenance and testing are essential to ensure that the emergency system is in good working order. By following these guidelines, you can ensure that the optional load is connected safely and reliably. When examining the options of adding a third subpanel versus installing a transfer switch, let us not forget to calculate the cost-effectiveness and long-term maintenance of the solutions. Depending on the long-term needs of the installation, one option will shine over the other. It is important to document the decision-making process and to be transparent with all stakeholders involved. The calculations for voltage drop and conductor ampacity are also vitally important. We must ensure that the conductors are appropriately sized for the intended load and length of the run to minimize voltage drop. Voltage drop can cause equipment to malfunction and can also reduce the efficiency of the system. The NEC provides guidelines for calculating voltage drop and conductor ampacity. Section 215.2 of the NEC covers feeder conductor ampacity. The feeder conductors must have an ampacity not less than the sum of the continuous loads plus 125% of the non-continuous loads. Section 310.15 of the NEC covers conductor ampacity. The ampacity of a conductor is the maximum current, in amps, that the conductor can carry continuously under the conditions of use without exceeding its temperature rating. Tables 310.16 through 310.21 provide the ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius. We must also consider the impact of harmonics on the electrical system. Harmonics are currents or voltages with frequencies that are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Harmonics can cause a variety of problems, including overheating of equipment, increased energy consumption, and interference with electronic devices. If the optional load is likely to produce harmonics, it may be necessary to install harmonic filters to mitigate these effects. We must also consider the impact of surge protection on the electrical system. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges, which can be caused by lightning strikes, switching operations, or other disturbances. Voltage surges can damage or destroy sensitive electronic equipment. If the optional load is sensitive to voltage surges, it may be necessary to install a SPD to protect it. We should also consider the impact of power quality on the electrical system. Power quality refers to the characteristics of the electrical power supply, such as voltage stability, frequency stability, and harmonic content. Poor power quality can cause a variety of problems, including equipment malfunction, reduced equipment life, and increased energy consumption. If the optional load is sensitive to power quality, it may be necessary to install power conditioning equipment to improve the quality of the power supply. When adding a new load to an existing electrical system, it is important to consider the overall capacity of the system. The existing electrical system may not be able to handle the additional load. It may be necessary to upgrade the service entrance, the panel boards, or the wiring to accommodate the new load. A load study should be performed to determine the existing load and the anticipated new load. The load study should take into account all of the loads that will be connected to the system, including lighting, appliances, and equipment. The load study should also take into account the demand factors for each load. Demand factors are used to estimate the average load over a period of time. The NEC provides demand factors for various types of loads. Based on the load study, it can be determined whether the existing electrical system can handle the new load. If the existing system cannot handle the new load, it will be necessary to upgrade the system. The upgrade may involve replacing the service entrance, the panel boards, or the wiring. The upgrade should be performed by a qualified electrician. Remember to always prioritize safety when working with electrical systems. Electrical work can be dangerous, and it is important to take precautions to protect yourself and others. Always disconnect the power before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable codes and regulations. If you are not qualified to perform electrical work, hire a licensed electrician. When adding an optional load to a generator, be sure to consider the following: 1. The existing generator capacity. 2. The type of load. 3. The wiring requirements. 4. The safety requirements. And 5. The code requirements. By taking these factors into consideration, you can ensure that the optional load is added safely and reliably. Furthermore, remember to thoroughly test the entire system after the installation is complete. This includes testing the generator, the transfer switch, and the optional load. Verify that the system operates as expected under both normal and emergency conditions. Document all test results and keep them readily available for future reference. Finally, provide clear and concise instructions to the building owner or operator on how to operate and maintain the emergency power system. This includes instructions on how to start and stop the generator, how to test the system, and how to troubleshoot common problems. Proper training and documentation are essential for ensuring the long-term reliability and safety of the system.